Okay, so now I want to, I forget which question this is, but I think it's question 4. Or, yeah, question 4. I want to solve the equation that t derivative of u is equal to the double x derivative of u, 0 less than or equal to x, less than or equal to pi. I'm going to have an initial condition, u of x is 0 is equal to f of x, but now my boundary conditions, the x derivative of u at 0, sorry, I don't know what I'm going, yeah. The x derivative of u at 0 is equal to the x derivative of u at pi, and that's equal to 0 for all time. Okay, so what we're modeling now is we're modeling this situation. Well, what's going on here? I know the x derivative is equal to 0 at the boundaries, but remember, the x derivative, the flux, is equal to minus alpha times the x derivative. So what I'm saying is that the flux is equal to 0 here, and the flux is equal to 0 here. And the standing assumption is that it's insulated laterally, so there's no heat flow going up, down, in, or out, only left and right. But the flux here is equal to 0, so there can be heat flow inside the bar, inside the bar going this way, that way, or whatever. But there is no heat flow going that way, there's no heat flow going that way, there's no heat flow going in that way, or whatever. The boundaries here at the left endpoint and the right endpoint are insulated. Okay, and we're going to follow the steps that we did yesterday to find product solutions. Or not yesterday. I forget. It doesn't. I don't know when you guys are watching the videos. I didn't even do it yesterday. Yesterday is just no way the right thing for me to have said there. Anyway, we're going to try to find product solutions. U of xt equals h of t phi of x. We're going to plug these into the PDE. When we plug them into the PDE, we're going to get h prime of t phi of x is equal to h prime of t phi double prime of x. Okay, rearranging, we're going to get h prime over h is equal to phi double prime over phi. Okay, so again, function of t, function of x, they're equal to each other. They must be equal to a constant. We're going to call it minus lambda. Now I'm going to look at my equation for phi. Now here's where things will get a little bit different. I've got phi double prime is equal to minus lambda phi. But now my boundary conditions are going to imply that phi prime of 0 and phi prime of pi are both equal to 0. Now I'm going to leave this to you to show that lambda has to be a real number and greater than or equal to 0. Same exact or very similar argument as what I did for when we had phi of 0 and phi of pi were equal to 0 instead of the derivatives. However, lambda can be equal to 0. So I will leave this to you. If lambda is equal to 0, then the solution, which I'll call phi sub 0 of x, is just equal to a constant, which I will just call a for now. I'll call it a sub 0 for now because the 0 is there. Okay, so if I plug in a, if a is a constant, if I have a constant here and lambda is 0, it definitely satisfies the PDE, and the derivative of this function is 0, so it also satisfies this. So in other words, when I have boundary conditions where the derivatives are equal to 0 rather than the function, constant functions are allowed to be solutions because they no longer have to be 0 at the endpoints. It's just their derivatives have to be 0 at the endpoints. Okay, otherwise, the solution to this equation, the general solution, is going to be a cosine square root of lambda x plus b sine square root of lambda x. Now, if I plug in, so my boundary conditions are about the derivative. So I need to find the derivative first, and phi prime of x is minus square root of lambda a sine square root of lambda x plus square root of lambda b cosine square root of lambda x. So then phi prime of 0, what happens if I plug in 0 here? If I plug in 0, well, the sine term goes away because sine of 0 is 0. The cosine term is 1. I'm assuming now that lambda is greater than 0, so that implies b is equal to 0. So that term goes away. So I'm going to remove this term. Okay, on the other hand, if I plug in pi, this is equal to 0. But if I plug in pi here, this is equal to 0. Well, if b is equal to 0, a cannot be equal to 0. Because if a was equal to 0, phi would be trivial. I don't care about trivial solutions. So I can divide both sides of this equation by a. I get this. Minus lambda, or minus the square root of lambda. Lambda is not 0, so the square root of lambda is not 0. I can divide both sides by that, and I get sine of the square root of lambda times pi is equal to 0. Well, again, the only way that this can happen is if square root of lambda pi is equal to k times pi, and if k is greater than 0, this means lambda has to be equal to k squared for k equals 1, 2, so on and so forth. And even for 0, it's that as well. Okay, so now we've got for lambda equals k squared, for k equals 1, 2, so on and so forth, phi k of x is going to be equal to cosine, is going to be equal to ak, I'll call it ak, cosine kx. Alright, so that's the phi equation. Now I need to look at the h equation. If I look at the h equation, I have h prime is equal to minus k squared h for k equals 0, 1, so on and so forth. Okay, if k is equal to 0, it's h prime is equal to 0, which means h is a constant. If k is bigger than 0, we're going to get h of t is equal to a constant, which I'll just call c for now, e to the minus k squared t. Notice if k is equal to 0, I get a constant, so this formula works. K equals 0, 1, so on and so forth. So then down here, I get hk of t is equal to e to the minus k squared t. I'm not putting a constant here because when I multiply these two, the ak will take the constant. Okay, so now the idea is, what if I can write my solution as a sum of these product solutions? So in other words, what if I have u of xt is equal to the sum k equals 1 to n, k equals 0 to n, ak e to the minus k squared t cosine kx. Well, now following along what we did yesterday, I'm going to note that if I plug in t is equal to 0, this is f of x, but the exponent goes away. So if I look at the integral, from 0 to pi of f of y, now I'm going to do cosine of ly, okay, because I've got cosine in my sum here. Well, again, following very closely to what I did yesterday, I keep saying yesterday, I don't know why. This is going to be equal to the sum L equals 0 to n, the sum k equals 0 to n, ak, and then times the integral 0 to pi, cosine kx, cosine ky, cosine ly, dy. Now this integral is equal to 0 if k and l are not equal to each other. It's equal to pi if k and l are both equal to 0, and it's equal to pi over 2 if k is equal to l and it's greater than 0. Okay, then so overall, this sum is only going to be non-zero when k is equal to l. And in that case, we're going to get a sub 0. If I'm in the k equals l equals 0 case, this integral is going to be pi, and so a0 is going to be 1 over pi times the integral from 0 to pi, f of y dy. And then for k bigger than 0, the integral is pi over 2, and so ak is 2 over pi times the integral from 0 to pi f of y cosine of ky dy. Okay, and so now this is as far as we can take the problem because I don't know what f is, so I can't actually compute the coefficients. So this is my formula for u of xt, and this is the formula for the coefficients here. You just plug those in to get the solution. Okay, that's it. Later on, not today, Wednesday, I'm not going to do this, but later on I'm actually going to, I'm going to do a wave equation example, and then I'm going to do an example where we actually have a formula for f of x, and we're going to try to get explicit formulas for the coefficients. But that's all I have for today.